So hello everyone, I'm Theo, and in this presentation we are going to talk about non-uniform mesh sampling, and in particular fast sampling in GPU. So I'm not the main author of this work. Actually, Jeremie did most of the work while interning at Adobe, but unfortunately he's currently teaching in Mongolia, so could not attend this conference. So what are we talking about non-uniform mesh sampling? Like the setup is that we are starting from a mesh with a density map, and we want to generate random sample on the surface according to the distribution of the density map. And like this work was motivated by purely procedural geometry and how to distribute fibers onto a surface, but this kind of like process has a lot of application in, for example, for mesh instancing, light sampling, or simply as an integration for a more advanced sampling like blue noise sampling. And of course, because we are at HPG, the question is how can we do it real fast on GPU, and in particular, how can we reach like 10 billion samples per second. So there is surprisingly not much work, not previous work on non-uniform mesh sampling. The traditional approach is to use rejection sampling, and it has two flavors. The first one assumes that we are given a target sample count, which means like the density is only relative. Right? We want like this region to have twice as much sample as this region. And the other flavor is simply that we want the sample count to emerge from the density, which means like the density is actually absolute. So, for example, in sample per meter square or something like that. And there is like we only found like one previous work working on this specific setup, which is fast random sampling on triangle meshes by Sik and Krivanek. And all of these methods work differently, and let's iterate through them. So, for example, in a case we are given a target sample count, the traditional method is to just have like one thread per sample, and each thread is going to generate sample candidates on the surface in a uniform manner, and simply accept it or reject it depending on the value of the density at this location. So what we have is basically like a non-uniform, like a non-local unbounding loop for each thread, where like basically we are jumping around in a mesh until we accept the sample. When the sample count is emerging, the strategy is typically to first create a bunch of sample candidates over the whole surface in a uniform manner, according to basically like the maximum density of the mesh. So we really need like a large sample of candidates, and simply like accept or reject each sample based on a single lookup. And the work of Sik and Krivanek basically instead of using a rejection sampling like method, subdivide the mesh until they reach like a constant density over a triangle, which is, of course, is very easy to sample, but requires a lot of memory, because you can imagine that if you have like a very high-resolution density map, you have to really subdivide a lot to reach a constant memory. So all of those methods are different shortcomings that we are trying to address in this work. In particular, we want to, we are still doing rejection sampling, but in a more local manner, and with that respect, we're able to reduce the size of the loop for rejection sampling. We don't need any large upfront memory allocation beforehand, and we don't need like memory during sampling, additional memory during sampling. And while still relying on like some kind of preprocessing, it's very lightweight and can be done at every frame basically. So how does it work? Well, our approach, like the main idea, is to split the sampling problem into independent subproblems, and typically use the fact that triangle meshes, a triangle in a triangle mesh, is basically like a native stratification of the surface. So here, like we use stratified sampling where triangle act as strata, which means that we have to compute density integrals over triangles, and we do it efficiently using hardware rasterization. And as part of this process, we also have to compute the area of the overlap between like a pixel and triangle, and we have to do that a lot of time. So doing that in a GPU-friendly manner is crucial. Then, at some point, we of course need to regroup all those per triangle information into like one single data structures. So that's where we introduce an unordered cumulative distribution function to do that efficiently. And finally, we will generate the samples, and because it's stratified sampling, all the sampling process is very local and much more efficient. So let's jump into the stratification. And typically, because we want to basically know what's happening for a given triangle, we need to find out the emerging sample counts per triangle. So the formula for this sample count per triangle is quite simple. And the hard part of it is basically just computing the average density or the density integral over this triangle in texture space. And the question, of course, is how to do that efficiently. And if we actually expand this formula, it's basically the sum of, assuming like nearest neighbor sampling, is basically like the sum of over all the pixels that overlap this triangle of the density of this pixel and the area of the overlap. And if you look more closely, like this sum is basically exactly rasterization in UV space, which gives you all the pixels that overlaps this triangle in texture space. And of course, this area means that we will have to deal with this textile triangle overlap in an efficient manner. And here, like the whole idea is like to, instead of doing stratification where we like assign one thread for each triangle and do stuff independently per triangle, here, by doing rasterization, we are basically assigning one thread per pixel, which is a much finer granularity, and it's much more faster. So in more detail, by doing this rasterization in texture space, we of course want to do conservative rasterization because, for example, one pixel can belong to many triangles, and we still want to consider the contribution for all those triangles. And it does require no depth attachment or no color attachment. Our only outputs are buffers that basically compute like the per triangle density, like the per triangle average density and the per triangle max density, which will be useful to reduce the loops, like the length loop of the population sampling. So which means that, of course, here each thread is actually considering like so like one pixel here. And we have like two atomics per fragment, so one for the max density and one for the average density, which is, of course, like kind of cheap in current GPU, but still is a bottleneck. So instead, what we are using is assuming the fact that we can actually use subgroup intrinsic in a fragment shader. And what we do here is that, for example, if all the threads from a given subgroup belong to the same triangle, we can perform like subgroup reduction using like the subgroup intrinsic if possible. And if it's not possible, we simply fall back to actually using those per fragment atomics. We actually try to use a finer granularities, for example, in the case here at the bottom where like a warp or like a subgroup spawn across like 3 different triangles. We could perform reduction like per like subset. But we found out that with using, like, for example, like this cluster or the NVIDIA partition, we didn't see any clear benefits in our case. So moving on to the next step is how we actually compute this triangle square area overlap, which seems like a very simple problem. But actually, like the resulting polygons can have like many various shapes. So from like basically like any polygon from 3 to I guess 7 edges, or also like could be empty. So, of course, that running in a fragment shader is kind of not very good because of divergence, because of a lot of different cases can happen. So instead of looking at this problem from a geometry processing perspective, we instead take a signal processing approach, which is kind of novel, using only convolution, using the fact that the area of the overlap is basically evaluating the convolution between the triangle in texture space and the indicator of a square, that we can evaluate it pointwise. So here, for example, the convolution is like the red function on the right, and by only evaluating this function pointwise, we can get this overlap. But of course, like the challenge here is that like the triangle indicator is not that easy to work with. And in our case, we want to have like a triangle indicator which is both plays nicely with integral, so we want it to be a sum rather than a product. And of course, we want to also play it nicely with the convolution, because we are stuck with this convolution. So the trick here is to see the triangle indicator as a sum of a per edge indicator, which look like this. So it's basically like minus half outside the edge, half inside the edge, and 0 outside the y range of the edge. And if you actually like look at the three of them at the same time and add their contribution, you can see that you can retrieve the triangle indicator. So it's exactly 0 outside the triangle and exactly 1 inside the triangle. And so bear with me with the moment because it's a bit technical, but if we actually look at the convolution first along the x-axis, what we get is a simple piecewise linear function that we can further simplify into a sum of two linear functions, which plays very nicely then for the y convolution. So putting all of this together, what we get is simply the sum of 6 simple closed form integral. And if you want to take a look at the actual code, you can see the Schertzer implementation at this link. So now that we are able to compute very efficiently those per, like the images sample count per triangle, what we want to do is not like have like one dispatch per triangle. We want to have like one global dispatch. So we need to find a way to combine this information, like this local information into like a global data structure to assign basically for each sample a single triangle. And this is kind of equivalent to sampling a discrete probability distribution, which means that from, for example, like here, this input array, we need to compute its cumulative sum. So there is, of course, like a bunch of literature on how to compute efficiently cumulative sum on GPU, which either are simple to write but requires like multiple kernel calls, or requires like a single kernel call, but are quite complex to write and only reach peak performance at a very high regime. So like a very large number of triangle in this case, which is typically way beyond the range of typical application for sampling. So instead, what we want to have is basically the best of both worlds by having like a single pass and a very simple to write code. And the intuition behind that is that when we want to sample a discrete distribution, the order of the elements, or in this case, the order of the triangles, that not really matter, which means that instead of fighting against the unspecified thread shading nature of GPU, we just embrace it and deal with it. And which means that we are actually computing here like an odd order cumulative sum, which is basically computing the cumulative sum as if the input were permuted. And of course, we also need to compute the inverse permutation to be able to use this cumulative sum. So how does it work in practice? Well, starting from our input per triangle count, we want to, of course, output the cumulative sum and the inverse permutation. And for that, we need like two global counters, one for the partial cumulative sum for the samples, and one that counts like the number of triangles processed so far. So for example, let's say like the first triangle to process is this one. Well, we simply do an atomic add for these two counters, and that gives us where to write on the output cumulative sum and the values. So here, of course, what we get is the exclusive values. So we need to add the values from the buffer first to actually have the inclusive cumulative sum. And if we do that iteratively, I mean, of course, in parallel, but the atomics are performed iteratively. We fill the buffer until like we actually get our output. But here is one catch: is that like those two counters need to be updated synchronously, which is not possible on current hardware easily. So the trick here is just combine those two counters into a single one. Like a single 64 bits global counter by packing like the two integers into one and unpacking when writing the value. And a little bit of implementation details is that, of course, like here it requires like one atomic operation per thread, but of course we can simplify this as the recitation pass by just doing subgroup intrinsics. So not looking at the actual generation samples, it's just a simple rejection loop, but with very low divergence and very memory cache friendly, because what we have here is basically like a bunch of threads that are processing more or less like the same triangle at the same time within the same subgroup, and are doing memory fetch into like the same local region in texture space. So that's very efficient. So if we take a look at the result, we use like a benchmark over the Gaussian product of like a number of density and meshes, and we compare against plain regression sampling, of course, like the fast regression sampling of Sek and Krivanek, and we also compare against a native triangle stratification, which is basically like doing the stratification, but without all of our improvement. So here we report like the average and standard deviation across data sets, and what you can see is that for medium to high sample count, we are basically like 1 order of magnitude faster, which is pretty good. And if we look at the actual components, we can also see that basically like the doing our text cell triangle overlap instead of the actual geometry processing approach is again 1 order of magnitude faster as well during the suggestion. And for the cumulative sums, we are at least as fast as the decoupled logback, which is much harder to write, whereas ours only take like a few lines of shader code, but of course is unordered. And if you look at some results, we can see here, for example, this is an example where we treat the emissive map of a material as like a light density, which can help like Monte Carlo light sampling. So here, like the density is updated at every frame, and of course the sample are recomputed at every frame as well. And here is an example of geometry instancing, where again, like the position on the surface drive like the position of the instances. Of course, there's a few limitation, which is still like a rejection sampling approach. So if you have like one white pixel over like a 8K density map, it will be hard to find with rejection. But we can still see that future work might address this stuff by actually processing like density map with, for example, multi-scale and with some kind of adaptive subdivision. And of course, like we think that the triangle text cell overlap approach might apply to like a wider class of could have more application to different shapes and even in this like setup. So in conclusion, we introduce a fast non-uniform mesh sampling method, which use like hardware like rasterization to do like stratified sampling over triangles with GPU-friendly triangle text cell overlap and an efficient order-breaking cumulative sum. And we actually reach our 10 million sample per second on this laptop. And thank you.
Okay, we have some time for questions. Let me see if I can spot any hands up. Oh, yeah, I see one there.
Hi, so thanks for the presentation. So one question I have is like, one of the problems you're facing is like you have like a non-uniform distribution of the geometry and the triangles. You don't know which are mapping to the distribution, like which triangles we need to get subdivided or not. And the problem that you're trying to resolve here is basically, right, you are traversing the triangles, you're looking if that one needs work or doesn't need work, and then you try to find like how to do the work, right? And the question I have is like, did you look into like workarounds which would be allowing you to adaptively like look at a triangle, is it big, is it small, how much work do I need to probably spawn for this triangle, and just create as many threads as you actually need dynamically?
So basically, you can see that as some kind of spectrum, right? So on the pre-processing side, where you want to look what's going on at like for each triangle, like at what level you need to check the density is what was done by the previous work. In our case, we look at the other side of the spectrum. It's like we actually need to consider every individual pixels. So we need to actually look at the middle ground, but I think yes, that one future direction of work is like to look at the middle ground. So is there like a way to do like a first pass to actually look where we actually need to consider every pixel for the triangle, or where we could look like something much smarter. For example, if the density is uniform for a triangle, maybe like we actually don't need to sum all the like pixel one by one. So it's future work, but yeah, that's definitely something we could do. Right. So for example, using like multi-scale approach or this kind of stuff.
Thank you.
Someone else? All right, nice. So I don't have to run around.
Thank you. Nice presentation. I was wondering if you had also considered alias tables for the discrete sampling problem, and if so, what your thoughts were there.
Yes, so as you can see, what we used in the end for doing the sampling process was to use just like a binary search over the CDF. And typically, what previous work was doing was to actually like either pre-compute the inverse CDF or doing the alias table. But in our case, because we have somehow assumed that we have like way more samples than triangles, what happens is that during the sample generation, because the work was done is has very low divergence, like the cost of actually doing this binary search is very cheap. So like there is no need for extra data structure, and basically like the cost of pre-computing this data structure, so either the alias table or the inverse CDF, will not like worth it.
Okay, makes sense. Thanks.
All right, let me go back to the center. So, one last question. I think we have time. Let me see. Okay, I'll have one for you actually. You know, this is great for random sampling, but of course in computer graphics we all like our low discrepancy blue noises. Which do you have like ideas of which algorithms would be compatible or amenable to similar kind of ideas?
I'm not sure if that could be directly applicable, but what I can say is that all the most advanced sampling techniques basically need an initialization, and this initialization is typically done using uniform sampling, or in like this case non-uniform sampling if it's like driven by a density. So I think that this can be just like plug and play for at least the initialization part. I don't know if this can be adapted directly, for example, like to blue noise sampling. I'm not sure, but at least only like for the first part. That
makes sense.
That's an easy win.
All right, thank you. Let's thank our first speaker.